All right, so we're reviewing a little bit more work, power, energy stuff. There's some tougher problems on this one, and a power question as well, which we haven't seen yet. So a lot of these are still three variable equations here. So here, the big idea is if I can pick out the labels. So 50 newtons, that's force, and distance is 3 meters. Well, and I have my equation, work is equal to force times distance. That means that all I have to do is work, I'm going to clear it. Work is equal to 50 newtons times 3 meters, which is going to be 150. What is my units? Joules. Okay. But it also asks me about power output. Okay, so then there's a second problem here. Well, power is equal to work divided by time, which is equal to then 150 joules divided by 0.9 seconds, which should give me, if I do this right, 150 divided by 0.9, 167, and I'm rounding, and the unit is watts, which is a W as well. But it's an italicized W for watts. So there you go. So Skippy does a push-up. Mass is 70 kilograms. Pushes up 0.5 meters. How much work? We're going to assume we're just counting 1.5 meters here. You could make an argument that the distance should be 1 meter because you go down 0.5 and then up 0.5, but I'm going to say 0.5 meters. Force here is mass times gravity. That's the weight, right, which is equal to weight. So I got 70 kilograms times gravity, which is 9.8 meters per second squared. So I end up with a force of 70 times 9.8, which gives me 686 newtons of force. Okay, so then here, work is equal to 686 newtons times 0.5 meters, which is equal to 0.5, 343 joules of work. And it says also if he does 10 push-ups, so I'd have to take, this is equal to 1 push-up. Now if I want to do 10, and then times 10 is going to give me 10 push-ups, which would be 3430 joules for 10 push-ups. Okay, so you got two answers there. I'm going to bold that so it's a little bit easier to see. Okay. So Jimmy's about to sled down a hill, 20 meters high, in mass 70 kilograms. How much potential energy does it have? Well, mass is 70 kilograms, just like in the above one with Skippy. Height is 20 meters. So I got mgh here, so my mass is 70 kilograms times 9.8 meters per second squared. Sorry, this should be a parentheses. Just so you can see each variable pretty clearly here, times a height of 20 meters. It's going to give me 70 times 9.8 times 20 gives me 13,720, and it's energy, so joules. Brock is driving his go-kart with a mass of 1,000 kilograms at a velocity of 35 meters per second. How much kinetic energy does he have? Well, kinetic energy is 1/2 times mv squared. So when I'm calculating here, I get 1/2 times mass, 1,000 kilograms, times v, which is 35. But I have to square 35 first. So mathematically, I'm just going to do this step so it's pretty easy to see. When I take 35 squared, I'm going to get 1,225. So you can see that order of operations, PEMDAS, that's what you'd have to do. Do your exponents first. So multiply all those out. I'm going to get 612,500 joules of kinetic energy. Okay. Now, here I worked this one out a little bit so you could see. Baseball's resting on a shelf. Say you got a an autographed baseball, how much potential energy does it have? Well, that's potential energy is mass times gravity times height. Gravity's there, so mass, gravity, and height. Multiplied out, not a lot of energy. But numbers 5 and 6 play into number 7, so that's why I'm putting them all together here. Right before his ground, all his potential energy has been converted into kinetic. So the big idea is that 0.294 joules of energy, that amount of potential energy becomes all of the kinetic energy at the bottom. So for number 5, the potential energy is equal to this many joules. From number 6, we remember that all potential becomes kinetic right before it's the ground, so that means my kinetic energy is really equal to 0.294 joules. I also know that kinetic energy is equal to 1/2 times mv squared. So I've done some of the work here already. So all this to be said, I'm plugging in the amount of potential energy I got here to become kinetic, and it's 1/2 times m times v squared. Well, I need to solve for v. Okay, so that means I'm plugging in Ke, 1/2 is the same, mass is 0.015 kilograms. So first I have to multiply these two numbers to get 0.00075. I'm actually going to draw here because I think it's going to be a little bit easier for you to see me do it this way. Okay, so I'm not quite done yet. So after this step, I need to divide both sides by 0.0075. Okay, so I divide both sides by that, 0.0075. It's going to take me a little bit longer to do this, so I apologize for that. So 0.0294 divided by 0.0075 is equal to, I'm going to go back to text here for a minute. Take it back, I'm going to draw. It's equal to 3.92. So 3.92 is equal to, and right here, those numbers cancel out. So it's equal to v squared. So how do I get the v by itself? I have to take the square root of both of these numbers to give me my value. So on my calculator, I'm just going to hit square root of, where are we at? There we go. Square root of 3.92. It's going to give me 1.98. And its velocity, so it's going to be meters per second, is going to be equal to my velocity. So on this side, the squared and that cancel out. Okay, so that's what's happening when I take the square root there. That's a tough problem. That's about as hard as it gets. Okay? So a lot of conservation energy says that energy cannot be created or destroyed. It can only be transferred. And that's what we see in these problems right here. All of the potential becomes kinetic, which causes that speed to increase, that velocity to increase. So if I had a roller coaster, this is what it's asking me, and I'm going to draw a little diagram here, is if I had a roller coaster that had a big hill like this, okay, where I'm starting at the top of this, I'm going to start right here. Start at the top of this hill, I go down. It's saying, could I come up to the top of this hill? If I start here, would I be able to go down and then up all the way to the top? That's the question. And the answer is no, because all this PE becomes K kinetic energy down here, but that means the max height that I can get to is that height right here. That's its max height. So it won't ever be able to go up any higher because you can't take all the potential, convert it to kinetic, and then somehow get more potential. It can only be converted to a different type. It can't be created or destroyed. And that's what that question is trying to get at there. So when talking about mechanical energy, two forms are potential, which is stored, and kinetic, which is moving. So this is kind of conceptual piece. You have two people, a person with more mass, person with less mass. Who has to do more work to climb a ladder? That'd be the big guy, because work is force times distance. They're climbing the same distance, but force is mass times gravity, so the person with more mass will have to do more work. If I climb a ladder fast or slow, which one's doing the more work? It's the same work, actually, because it just depends on force and distance, not time. But power depends on time. Power is work divided by time. So if I go fast, it means my denominator is smaller in that equation. So I'm going to have higher power. Energy is measured in joules. Okay. Food and pop labels, energies are measured in calories, which is actually a kilocalorie. Yeah, it's confusing. I probably won't get into that right now. But understanding that's where the energy is coming from. Power is work divided by time. So I got 1,000 joules of work in 8 seconds. Work divided by time. I divide 1,008. I get 125. What? I get 125, excuse me, watts of power. And you'll see those on something like light bulbs. It's telling you how much energy per time is able to be expelled. And as you notice, a higher wattage means the light bulb can get brighter. So if you have questions, let me know. This one has some more complicated problems on it.